So now this brings us to our first big application section, related rates. Now up until this point, most of Chapter 3 has been focused on repeatedly asking and answering the same question. Here's a new type of function that doesn't fall under one of our existing rules. How are we going to take its derivative? Right? That's pretty much what every section has been about, starting with section 3.2. In 3.2, it was products and quotients. So we have the product rule and the quotient rule. In section 3.3, then it was trigonometry. How do you differentiate sine, cos, and tan? 3.4, now we want to know how to deal with composition of two functions, right? So that's how why we introduced the chain rule. 3.5, it was exponential and logarithmic functions and so on. But now that brings us to the situation where we're now going to put that to use and solve some real life problems. And really, what it comes down to is that smooth functions arise in nature all the time. Any quantity that changes over time can be modeled as a function of time. Sometimes they'll be continuous, sometimes not. Of the ones that are continuous, some of those will be smooth and some will not be. Smooth is in differentiable, right? So the ones that are smooth, we can differentiate them with respect to time, because if we've modeled them as functions of time and they're smooth functions, we can take their derivatives. So let's start by looking at the notation that we're going to use. So if x and y are let's say two quantities which vary over time, then we can model them as functions of time. But let's just say that that's automatic. So let's say that if x and y are differentiable functions of time, so assume that x and y are two of the ones that happen to be smooth, then this is the notation that we'll use for their derivatives with respect to time. And this is nothing new, but this is just a new way to use existing notation. So if I write dx dt, well, I've already introduced this notation, but let's practice reading it out loud anyway. Dx dt, that just means the derivative of x with respect to t. So in other words, the derivative of x with respect to time. Really what that's representing, though, is the rate at which this quantity is changing over time. So let's just say this is the rate at which x is changing. So we'll just write these down carefully to give ourselves an opportunity to get used to this. And then same thing for y. If I write dy dt, that's the rate of change of the variable y, or the rate at which y is changing. And often we'll start by looking at relationships between several quantities, and then from that we can get a relationship between their rates of change. And that's typically how these problems are going to go. Now I want to start, before I get into any of the actual application problems, I want to start with a warm-up which really shows you how to deal with the mathematical model, because what you see here is a very abstracted problem. There's no real life quantities. You don't see things like volume, velocity, or length, radius, surface area. You don't see those real life quantities in this problem. That's because the mathematical details have been abstracted, and that's actually going to be your goal when you're dealing with word problems, is to actually abstract the mathematical model so you can work with that directly. So the purpose of this example is to show you how we can work with a model once we've extracted it from a real life problem. And then starting from the next page, our goal will be to take real life problems and turn them into problems like this. And then we can solve them using the method I'm just about to show you. Okay, and really, what we're going to put into use here is implicit differentiation, the things we learned in the previous section. The notation is going to look slightly different, but that's because we're going to be differentiating with respect to a new variable now, which is time. So here's what we have. We have a relationship between two variables, x and y, and it kind of seems like the way this is written, you can see that y is written as an explicit function of x, but if you can see there's a little bit more here. It says let y be the square root of 2x plus 1, where x and y are functions of time. So yes, y is a function of x, but it's also the case that x and y themselves are functions of some external variable, time. Okay, so for part A, what are we asked to do? We're asked to assume that the rate at which the variable x is changing is given by 3. So there's no units in this problem because all that's been abstracted. But in general, usually you would associate this with units somehow. It might be in centimeters per second, or it might be in pounds per minute. It depends on the context, right? But we don't have the context here, so that's why you don't see any units. Okay, but anyways, we're asked to assume that dx dt is equal to 3 numerically, and then we're asked to find the rate at which the variable y is changing at the particular moment in time when x is equal to 4. Actually, I would really like you to pause this video after. I'm going to say that one more time, but then after I do that, pause the video and just say it out loud to yourself. It's really good practice, and I want to get you in the habit of reading these things in that manner. So read this as, find the rate at which the variable y is changing at the particular moment in time when x is equal to 4. So notice instead of just saying when, I said at the particular moment in time when x is equal to 4. And that's really how you should interpret that word when here. I'm using the word when just to keep things as brief as possible, but really that's how you should interpret it. Okay, well how are we going to solve this? That's the question. So let's do that. So we're going to start by looking at our relationship. We've got y is equal to the square root of 2x plus 1, and we're going to take the derivative of both sides of the equation, just like we did in the previous section, but we're not going to differentiate with respect to x this time. We're going to differentiate with respect to this external variable time, since both x and y are functions of time, as we're told in the question. So let's take the derivative with respect to time of both sides of the equation. So that's what you get if you just write down what you're going to do. But now let's actually do it. So on the left-hand side, if we take the derivative with respect to t of the function y, well, what do you get? Well, you can't say much except just say the derivative of y with respect to t. Just change the notation. Right? Write the derivative of y with respect to t in Leibniz notation. This is operator notation, just write it in Leibniz notation. And then on the right-hand side of the equation, well, we've got a chain rule, right? So 2x plus 1 is our inside function, and we've got a square root on the outside function, so we're going to have to use the chain rule here. So what's the derivative of the square root function? Well, recall, I'll just give you a reminder. In the case of just working with square roots, so forget about the implicit differentiation. That adds an extra layer of complication to things, but if you were just dealing with the derivative of the square root of x, you can write that as x to the power of a half and do the power rule, and you're going to get 1 over 2 times the square root of x. Okay, so that's what we're going to take advantage of here. So if I differentiate the outside function and leave the inside function alone, I'm going to get 1 over 2 times the square root of 2x plus 1. But then, of course, I need to multiply that by the derivative of the inside function, which I have to do that with respect to t here because we're differentiating with respect to t. So that comes with us as well. So the derivative with respect to t of 2x plus 1. All right, so now, well, here, 1 over 2, my phone's ringing. There, hope it stops. 1 over 2 times the square root of 2x plus 1. This part's dealt with, but now we still have to differentiate the inside. So 2x plus 1. Well, what are we going to do with this here? Here's how you can tackle this. There's a little bit of space up here that I want to take advantage of because I don't want to take up too much space down in this solution because we need it for the rest of the problem. But if I take the derivative with respect to t of 2x plus 1, well, here's how I can do that. I could first just split it up as the derivative with respect to t of 2x plus the derivative with respect to t of the constant function 1. Now, what's going to happen over here is that 2 can be pulled right out of the derivative because it's a constant multiplier, right? So I can write 2, and then what's going to come after? It'll be the derivative with respect to t of just x, right? If I take the 2 and pull it out, all I'll have left in here is the x, and I'm taking its derivative with respect to t. So why don't we just use the notation for that, dx dt, right? And that's what I'm going to get for that first term. Now what about the derivative of 1 with respect to t? Well, 1 is a constant, so derivative is 0, so we really don't have to worry about that second term. Okay, so we're just going to get 2 times dx dt. Okay, that was just a little bit of side work just to do with our example down here. So let's take advantage of that now. So here, this is really just going to become 2 times dx dt. Okay, so we have dy dt is equal to 1 or 2 times the square root of 2x plus 1. Nothing's changing there. And we're going to multiply that by 2 times dx dt. All right, so now we've finished taking the derivative. Look for anything that you can do to clean things up. The 2's can cancel, right? So we're going to get dy dt is equal to 1 over the square root of 2x plus 1 multiplied by dx dt. All right, so that's good. Now, what about the problem, right? We're asked to find dy dt at the particular moment in time when x is equal to 4, and we're also asked to assume that dx dt is equal to 3. So let's do that. We're going to plug both of those values in. So first of all, dy dt, let's first take into account the fact that we're assuming that the derivative of x with respect to time is equal to 3. We're going to get 1 over the square root of 2x plus 1 multiplied by 3. So that's going to give us 3 over the square root of 2x plus 1. That's under the assumption that dx dt is equal to 3. Well, what about what we're asked for? We're asked to find dy dt at the particular moment in time when x is equal to 4. So we want dy dt when x is equal to 4. So what's that going to give us? We're going to have, well, just write out dy dt, but just plug in x equals 4. So we get 3 over the square root of 2 times, now x is equal to 4 plus 1. Right, and that just works out to 3 over the square root of 9. Because 2 times 4 plus 1 is 9. And then, of course, the square root of 9 that's going to be 3. So we really just have 3 over 3, which is 1. So in this case, that is our answer for part A. The derivative of y with respect to t when x is equal to 4 turns out to be equal to 1. Okay, and that was under the assumption that dx dt is equal to 3. We used which step did we use that assumption on? We didn't use that till this step, right? Everything down till this step was just done in general based on this relationship between x and y. And that's going to be important to note in problem B, that up until we got to this step, we still had not used any of the assumptions from part A. So really what that means is all of this work is also going to be relevant for part B. So for part B, well, in this case, we're making an assumption about dy dt. We're assuming that dy dt is equal to 5, and now we want to find dx dt at the particular moment in time when x happens to be equal to 12. Well, first of all, if we want to find dx dt, we probably want to use this relationship because it's got dx dt in it, but we're going to want to isolate dx dt. So how do you isolate dx dt? Just take the root 2x plus 1 and multiply it up to the other side. So if you do that, what you're going to get is dx dt is equal to the square root of 2x plus 1 multiplied by dy dt. All right, so, but we can go a step further now. Now let's use the information we're given here. We're assuming that dy dt is equal to 5. So let's actually substitute that in now. So dx dt is the square root of 2x plus 1 multiplied by 5. So really we're just going to get 5 times the square root of 2x plus 1. So then as far as our final answer goes, we want dx dt at the particular moment in time when x is equal to 12. So we're going to take this relationship and plug in x equals 12. So we get 5 times the square root of 2 times 12 plus 1. So 2 times 12 is 24. So when you add 1, you get 25. So we've got 5 times the square root of 25. The square root of 25 is just 5. So this is really just 5 times 5, which is going to give you 25. So that is what you get for part B. So this is just a warm-up. And if it's not immediately clear why this technique is important, not to worry. That's going to be made abundantly clear once we look at a few examples, where our goal is going to be to turn real-life problems into problems like you see here. And then how do we solve them? We're going to use exactly the technique that we just used here.